Hello and welcome students for today's lecture. So our course is what is happening? MA425 Topology, and this is lecture number 19. And there was one lecture in the beginning, the common one. So total 20 lectures. Okay, so this is the 19 lecture number for the course, and one was general lecture. And this is the last lecture before your midterm exam. Okay, so and I'm trying to discuss some important things, and then I will try to finish before the syllabus, before the exam. Okay, so now recall we define something called components, which is kind of a maximal connected subspace of the space. Okay, maximal means that if there is another connected subspace which contains that must be equal to that space. Okay, now we can define another such relation. So let me define properly. So let you have a topological space is be a topological space. Okay, and suppose we define the tilde on x. How so? So we say that 2 points are related if there exists a path joining x and y. Okay, now now our claim. So the claim is that tilde is and equivalent relation. Okay, equivalence relation, like we define for connectedness, right? Similarly, for with the help of path connected property, we can define this. Okay, now one first property was reflexive is simple, right? Reflexive. This is obvious because given any point x, that for all point x in x is already related to x, right? Why? Because you can define the constant map, right, from say 0 1 to x, and defined by take any points there and map it to x for all t belongs to 0 1, right? So this constant map is a constant function which map from x to x, right? So x is related to x itself. So this relation is reflexive, and you can obviously prove the symmetric property also similarly easily. Symmetric. So what does that mean? So so let x related to y, we need to prove that y also related to x, right? So if related to y, what does that mean? Then say there exists a path, say f from say 0 1 to x, says that what happened? Says that f of 0 is x and f of 1 equal to y, right? This is the meaning of path. Obviously this continuous map, right? Okay, so so we can define, so we define another map, so G from in same space, and we define by G of t equal to f of 1 minus t. Now obviously G is also continuous, right? If I define by this, so G is continuous, and not that G of 0 was what? So G of 0 was f of 1 minus 0, means f of 1 which is equal to y, and G of 1 equal to f of 0 which is 0, so which is x. So this is a path from y to x, right? So what does that mean? So thus G is a path from y to x, right? And hence y is related to x, right? So this is a symmetric relation, that is obvious. And then similarly, one can prove this is also transitive, and that is not difficult. Transitive. So what is given? Given that, say there are 3 points x, y, z, such that x related to y and y related to z, and we claim, what is my claim? Our claim is that x is also related to z, right? This is the claim. Now how do you prove? Now from the first hypothesis that there exists some f1 from say 0, 1 to x, okay, such that f1 of 0 equal to x, and obviously this is continuous. There exists a path. I should write down a path, okay, f1 of 1 equal to y, right? And similarly, because of second condition, there exists a path say f2 from, say, let me just write down say 1 to 2. See, I as I told you, path we can choose from anywhere to anywhere, right? So let me choose it from close interval 1 to 2 to x, such that f2 start at y and f2 finish at z, right? Clear? So this is also a path which start at y and z. Now you see that you have two continuous functions, and there is a common point 1 in this space where it is same, right? If a 1 equal to if 1 of 1 equal to y, similarly see I have 2 of 1 equal to y, right? So by pasting lemma, what you can say? So now using now remember pasting lemma the continuous function, what does it set? Pasting lemma, you can define a map, right? So you can define rather you can say paste the map. So define f from 0 to 2 to x, and how you define? So if you define f of t equal to f1 of t whenever t is in between 0 to 1, and f2 of t whenever t is in between 1 to 2. And you note that when t equal to 1, both cases they are same, the value is same, okay? So by pasting lemma, this f is a path, right? Is continuous and also satisfy the condition path from x to z. And this is the proof. So what does that mean? That means x is related to z. So this function is also, this relation is also transitive. So what does that mean? That means the way I define this, it becomes a equivalent relation, and hence you can talk about the equivalent class, right? So the definition, the equivalent class are the partitions which forms which coming from the equivalent relation. So this equivalent classes, or other whatever, yeah, so classes are called path components. So last time we defined component, here now we are defining path components, okay? Components, okay, of that space x. Is that okay? So example, so obviously we can have examples that so 1, 2, 3 closed, and then union open 4. Whatever you can choose. So you see that in this example you have two path components, this one, okay? This is not path connected, but it has two components. Okay, clear. So X has two path components. Okay. Okay. And obviously, the natural question one can ask that what can you say about the components or the path components? For example, for components, can you say anything about the topological property, like whether it's open set or closed sets? Okay, so you think about it. So maybe this the remark. Let me tell you something. Remark that whenever you have a space and you have components, then these components are always closed, right? So components of a space in any topological space are always closed in the same space, obviously. Okay, and I'm asking why. Just prove it. Okay, the proof is like probably one line or two line. Okay, so simple. Maybe I can give you hints. So to prove something is closed, you need to prove that. So if CB, so let me just give you hints. So hints you can easily prove after giving hints. So let C be a component of X, then so that C equal to C closure. Done. This is the thing, and then this is exactly simple to prove. Okay. Just recall that components are kind of maximal connected subset, right? So what does that mean? That means if you have any connected subsets which intersects with C, then C will contain that. Okay, and you know that closure of connected subset is also connected, right? So with the help of this, just one line you prove it. But what about the openness? Whether it is open? So the answer is may or may not be open. Sometimes it may be open, sometimes it may not be open. Okay. And similar question you can ask for path components. And so okay, but components are may or may not open. Okay, so may or may not open. Okay, now you just give example for each case. So example is, okay, so maybe I can give you. So for example, in my previous example, 1 2 union maybe 5 7 whatever I choose. So you see that the two components C1, which is close interval 2 4, and C2, which is close interval 4 5. So both are open in X. Both are open in X. Okay. But there are examples where the components are not open. So maybe I can give you another example. Say example 2. Say rational number. Okay. So this is a subspace R, and you see that what are the components here? The components are the singletons here, right? Singletons are components, right? So what does that mean? That means that that components are not open. Singletons in Q are not open, right? They are closed set. Okay. So what does that mean? That means so components are singletons. components are singleton sets which are not open. Okay, so you may have examples, right? For the case of path connectedness, you cannot say anything. At least connectedness, you can say that it is always closed. Path connectedness may be closed or may not be closed. Okay, so for path component, so but path components path components are may or may not, whatever, open or close. Can be closed, can be open. I mean, it can be anything. Okay. So this is your duty to find out an example where you have all these possibilities. Okay. Find out. Okay. So now, with the help of all this idea, we are going to define a space where we have a nice structure. So nice structure means that whenever you choose some kind of components or any open sets, any components, they are always open. Okay, they are always open, and this kind of space are called locally connected space. Okay, so let me define it. What does that mean? So locally connectedness. Okay, so let X be a topological space and X is an element of X. We say X is locally connected at X if for any neighborhood u of u of X. Choose any neighborhood u of X, there exists a connected neighborhood v of X such that v is inside u. So every neighborhood of u contains a connected neighborhood. This is the meaning of local connectedness, right? At X. So that is every neighborhood of X contains a connected neighborhood. Clear? And if X is connected, if it is locally connected everywhere, then X is called locally connected if X is locally connected everywhere. If is locally connected for all X belongs to X. Okay, then we say that X is locally connected. Clear? And so this locally connected property also tells you another nice things which you can define, that is called locally path connected. Okay, so I may say here locally connectedness and locally path connectedness. Okay, even you can choose path connectedness here. Okay, locally path connectedness. Okay, so how to define same thing? So X is locally path connected at a point X belongs to X if every so they are for locally connectedness. What is every neighborhood contains a connected neighborhood. Here, instead of connectedness, we will replace this by the path connected neighborhood. Okay, so every neighborhood of X contains a path connected neighborhood of X. Okay. And similarly, if it is true for every X, then it is called path connected. So X is called locally path connected, locally path connected if that property is true for if the above property is true for all X belongs to X. Okay, so that means for every points you have a every points X and every neighborhood of X you have a path connected neighborhood that contain the original neighborhood. Okay. Now let me give some examples. One can, the natural thing one can ask that what is the relationship between that connectedness and locally connectedness, similarly path connectedness and locally path connectedness. Okay, this is a natural question one can ask. Right, you can say that connectedness versus locally connectedness. For example, we have learned that path connectedness is a stronger property, right? Every space which is path connected also connected, right? So similar kind of thing is possible here or not. That connectedness and local connectedness, like something is more stronger than other thing, and the answer is these two are actually disjoint property. What does that mean? That means none of them is independent. So these two are independent to each other. These two ideas are independent to each other. So what does that mean? That means that all four options can be there. Four options means what? It can be both connected and locally connected, connected but not locally connected, not connected but locally connected, and neither connected neither locally connected. Okay, so maybe I can give an example one by one so you will understand. So both connected and locally connected space. Okay, so my laptop is getting heated. Yeah. Locally connected space. Okay, so you just to choose any these intervals, doesn't matter close or open, and so this is example of space which is both connected and locally connected. You can prove which is connected, and proving local connectedness is also simple. So what does that mean? That means if you choose any points in between this any neighborhood, you have a connected neighborhood inside that. That is obvious. Okay. Uh, yeah. So I mean, you just write down the proof properly. Proof is so simple. One line, two line proofs. Okay. Now next thing is let me give something locally connected but not connected. Locally connected but not connected space. Okay, so maybe this is my example, say 1 2, and then you choose say open interval 2 to 3, something like that. Okay. um, Now what is the advantage here? So the point 2 is not here, right? So this space is actually not connected, so this is not connected, so this not connected, but this is locally connected. Why this is locally connected? Because if you choose any points, so what are the options? Either there are two boundary points here. There are two. So minimum and maximum exist, right? So 1 and 3. And other than that, if you choose any points other than these 2 points, all the points are interior points, right? And hence you can find out the open neighborhood that inside the whole thing. And for the boundary point also, if you choose 1, then any 1 plus epsilon 1 to 1 plus epsilon will be open set, right? That contain the x and also is connected. So this is an example where you have a space which is connected and a locally connected but not locally connected but not what is that not connected. Okay, clear. So we have okay. So now let me give another example where you have the opposite one. So the opposite example. So connected but not locally connected. Okay, and the best example we usually learn is called topology sine curve. Okay, topology sine curve. Now recall what was that? So this is kind of you have so S, which is a collection of that x1 by x, and then you take union with that the line on y-axis from the unit line. So what does that mean? That means this is kind of point of the form 0 cross -1 to rather yeah, so -1 to 1, and sorry, this is S only, and this union this portion is the limit points of S, and this is S bar. Okay, S union this, and because S is connected, S bar is also connected, right? But this is not locally connected. Why it is not locally connected? Because if you choose a point, say for example on this line, so it's kind of haphazard here, and like this, right? And this is the line joining from this to this. Okay, now you see that if you choose so to prove this is locally connected, what you need to prove? You need to prove that for every points in a neighborhood you have a connected neighborhood, right? So you can find out points where you don't have any connected neighborhoods. Okay, inside that points to find out some points which does not have connected neighborhoods. Okay, and there's some neighborhood points and some neighborhood which does not have connected neighborhood. Okay, then you can find it. Okay, so one more example I can give you, which is the exactly opposite, like neither of those. And so number 4, so neither connected nor locally connected. And this is a simple example. I have only given Q is also R, right? Q is not connected obviously, and Q is also not locally connected also. So that is also obvious why Q is not locally connected, because the moment you choose a point and neighborhood, that if you cannot find any connected neighborhoods, because so given a point rational number inside Q, and if you choose any neighborhood, you see the components are singletons, right? So if for every neighborhood you have you have many components, right? So and those are all not connected each other. So these are all disconnected, right? So that tells you that Q is not locally connected also. Okay, so maybe okay. So after all those property, now we are in the situation to prove that main theorem, which I am going to state now. So the theorem is what? What was the theorem? So theorem is that a space is called is locally connected if and only if for every open set U of X, the components are, so you may have a component, right? So each components are open in X. So what does that mean? That means whenever you choose open set and there might be more than one components, and all the components are actually they open in X. So in particular you can say that U itself is a the components of U itself open, right? Because each components of I choose that every open set, every components of U. So in particular U itself, so X itself is open set, right? The whole space is open set. So it is true for X itself also, right? So in particular every components. So this is if and all, I mean this is for locally connectedness. Every components of locally connected space is open. Okay. So if I prove first one, second one will automatically prove. And how do you prove first one? So there are two parts, right? If and only. So let me first assume that X is locally connected. So let X be a locally connected space. Okay. And I need to show that and U say open set and U subset of X open. This is given to me, right? So you have a set and you open set, and so I choose some arbitrary components. So let C be a component end of U. So I need to show that C is open. That means So we will show that every point of C is an interior point, right? This is the meaning of open set. Interior points of C. Okay, so we start with the point. So let x belongs to C. So x is a point inside C, but U is open already given, so x also belongs to this, implies x belongs to U. Okay, but the property of locally connectedness tells you that for every open set containing a point, neighborhood a point, there exists a connected neighborhood, right? So thus there exists a connected neighborhood of x, say V, such that what happened? V is inside U, right? Content neighborhood is there, which containing in U, right? But see, B is intersecting C, right? But what is the meaning? So V intersection C is not empty, right? Because x belongs to both B and C, and C is the component. By definition, whenever some connected subspace intersect the components, then it contains full thing. This implies this contains C as V is connected and C is a component, right? Thus, so that is the proof. So you have open neighborhood containing the point. So that means x is an interior point. Interior points of C, and C is open, right? Now conversely also, converse part also you can prove. Conversely, assume that every open sets, every components are open. Conversely, and I need to now prove that x is locally connected. Okay, so let you choose a points. So let x belongs to so looking at terms means, so you choose a point and the neighborhood and then find out the current neighborhood, right? So let x belongs to x and U is so okay, so by neighborhood I mean open set. Okay, so I don't want to say anything, so use a neighborhood NBD of x. Okay, so now I need to find out that U contains another subset which is a neighborhood of x, and also which is open, which is connected, right? Now because U's element, U contains x and U may have a component, right? So you choose, let C subset of U be the components of U containing x, because every element of U will be one of the components, right? Containing x, right? So by the hypothesis, what is the hypothesis? Hypothesis tells you that every such thing has to be open, right? So C is component that containing x, and so the hypothesis tells you that whenever you have a components, that must be open. So hypothesis C is open. So C is open and C's component means is also connected, right? So thus uh, C is a connected neighborhood. Connected neighborhood of X such that C is inside U. So that means that X is locally connected. So this is the proof. The proof is simple, right? And similar proof is true for locally connectedness. The same proof, you just replace the connectedness by locally connected, path connectedness, and the proof is same, right? So similarly, next theorem. So next theorem you can say the similar thing. What is the next theorem? So you can say that X is locally path connected from a leaf. So a space X is locally path connected if and only if for every open set U of X, each path component. So there was a component, now we replace by path components. Okay, each path components sorry. Components are the components of U of U, each components of each component, not components. U is open, and the proof is similar proof. Okay, so how to prove? You start with first part is almost obvious. You start with a space which is locally path connected, and then you take a open set and then the components, and then you choose a point, so that will be sitting in some path component, right? And that path components is intersecting. So path component means what? So the same proof where you choose a components containing that, right? Similarly, here you choose a path components that contain the points, and because this is so the property of path component tells you that this kind of the maximal path connected subspace can be possible, right? So that will implies that these path components are actually inside you the space. Okay, and then and that is the proof. So that means you have a path component that contains that, right? Okay, and conversely you start with the opposite. So you start with the open set inside. So local path connected means you choose a point and you open set, and you find out that it contains a path connected neighborhood. The same proof will go through and you will the same answer, right? But the question is that do they have any kind of relation between these kind of components and path components? Like, are there like someone is connecting something or not? Okay. So for example, if you know something say locally path connectedness, can you say something about locally connectedness or not? Think about it. This problem is also interesting. So now I'm going to just give you an idea where you can check that relationship between components and path components. Okay, and this is the theorem. So theorem. So let X be a topological space space um, so each path components are kind of smaller. So what does that mean? So path components each path component of x lies in a components of x. X, that is given a path component that is sitting inside some component, an equality hole if and only x is locally connected. Okay, so equality hole mean they are same. Equality holes if x is locally connected. Locally, not if and only if x is locally connected. Now you can think that otherwise also obvious or not think about it locally connected. Okay, so now how do you prove this kind of theorem? So first part is obvious, so proof. So path components are, so let's you start with path components. So let P be a path component of x, and it takes a point, say x belongs to P, right? Now because x is a point of capital X also, so it will be sitting in some components. So let C be the component of x containing x. Okay, C contains x, and so what does that mean? That means okay, so now P is a path component means what? This is so what is the meaning of path components? Path components are also connected, right? So this is kind of maximal path connectors kind of thing, right? So as P is path connected, P is also connected, right? Because path connected are connected. And now see that P intersection C is non-empty and P is connected, so P has to be inside C fully, right? As P intersection C is non-empty and P is connected, C is a component, so P has to be inside C. P has to be inside C because it's component. Any connected subspace which intersects C has to be inside C, right? This we already proved last lecture. Okay. Now, and further, if it is locally connected, then what happens? So further, if x is locally connected, then what happens? Then we will claim that C further let x be locally connected. Then we will show that P has to be equal to C. So if not, then what happens? So if P is a proper subset of C, then you can find out some points, say x dash whatever, that be inside C but not inside P, right? And later you have some P1 is a path component component containing X tag. X tag, right? Because every point inside some path component, right? And this will implies that P1 also is sitting inside C, right? So what does that mean? That means you may have C may contain more than one path component, right? So you choose. So let you choose something. Say U is the union of all path components other than P, which is lies in C. Lies in C, right? I just show that if P not equal to C, then you have at least one such thing, P1, right? If there are more, then you take the union, doesn't matter. Okay, so once you choose those things, then what you can say that your C your C can be written as this P union of what was U. Let me write down different name because there are so many U, right? Maybe write down Q. This is easy. So P union Q. Q is the union of all path components of C, which lies in C, but is not equal to P. They are different from P, right? Now what happens? So this property tells you that the path component, because X is locally connected, all the path components are open. So as X is locally connected, all the path components are open, and hence Q is open, right? Hence both P is open, P is locally path connected, P is components, and inside the locally path connected space, so it's open, and Q is the union of path components. So union of open set is also open, right? And both P and Q are open. Okay. So we have open disjoint open non-empty subsets of Q. So what does that mean? That means PQ forms separation. So thus PQ forms a separation of C, which is contradiction because C is a component. Component means C cannot be separated. C is connected, right? Which is a contradiction, as C is connected, right? So what does that mean? So thus P has to be equal to C for when X is locally connected. Okay, and now you see that this is a property. You can easily check something is locally connected or not. If you know that a space has the property that the components and path components are not equal, then the space cannot be locally connected. Okay, so by this also you can check easily. Okay, I think I should stop here, and now all the best for your exam. Okay.